Here we are looking at lesson 1.5, segment and angle measure. So we are going to be talking about measure. And right away, talk about measurement a little bit. Measurement always requires a comparison to an accepted standard. We wouldn't be able to measure in inches if we didn't know what 1 inch was. We wouldn't be able to measure in meters if we didn't know what 1 meter was, or we wouldn't be able to measure weight in pounds if we didn't know what a pound was. So we have to have an accepted standard, and you are all familiar with those. So some of our standards, things that we use are centimeters or inches or miles. Those are all accepted standards. We have a ruler postulate. So remember, a postulate is a rule that we have in our system of geometry. It says every point on a line can be placed in a one-to-one correspondence with a real number, which is really helpful because no matter what you have a number line or any line, any point along here relates to some real number, and so we'll be able to measure things. The coordinate of a point on a number line is the number that corresponds to that point. So let's go ahead and slap some points on here or some values. So if we had point A right here, the coordinate of A is 1. And we say this is the graph of that. So just a simple number line. Length. The length of AB is the distance between its endpoints A and B on a number line. So we have a new notation here. We just have A and B right next to it. It does not have anything on top. It doesn't have a segment. It doesn't have a ray. It doesn't have a line. It doesn't have anything on top. When you see two points or names for points next to each other, it represents length. So often people forget that. So this represents a length. Well, how do we find the length between 2 points? Well, we subtract their values on the number line. So we do A minus B, and length is always positive. So what we have here is we have absolute value marks to show that our length will always be positive. Here we have absolute value. There's different ways to define this. This is actually more of a little bit of an algebraic way. The absolute value of x is equal to x or itself if x is greater than or equal to 0. So it's 0 or a positive number. I have it written right here. I was about to write it again. And it's the opposite. So it's itself. So the absolute value of 7, well, it's a positive number, so it's just 7. But if x is negative, it's the opposite. So if we had the absolute value of -7, -7 is less than 0, so we want the opposite of -7, which is just 7. So that's an algebraic way to think of absolute value. The geometric way to think about absolute value is that it is a number's distance from 0. A number's distance from 0. And since distance is always positive, the absolute value is always positive. Example 1, find the length of each segment. Well, segment BD. So maybe we'll mark these each time, but then get rid of it. So B is at -5 and D is at 3. Well, by definition up here, that I'll highlight, we can say the length, BD, so remember, if we want the length, we don't put the little segment above it, is equal to the coordinate of B, which is -5, minus the coordinate of D, which is 3, and then you take the absolute value of that. That's absolute value of -8, which is 8. Now, do we have to think of it in that way? We don't. We probably could look at this and realize, oh, it's 5 units to here, and too bad I can't count. This is a 2, not a 3, so now I need to go back and change these. And so the answer is actually 7, but we have a 5, distance of 5, another distance of 2, so total distance is 7. That's another way to look at that. All right, let's look at AE. AE, well, A, we have this is -5, -6, -7, -8, and E is at 3. And so again, we could say AE is the absolute value of -8 minus 3, which is the absolute value of -11, which is 11. Another way we could think is like, oh, I know this is 8 units and then 3 more units, so it's 11. So that's another way to think of that. And then EC. EC. So E is at 3. C is at -1. EC equals the absolute value of E's coordinate, 3, minus C's coordinate, -1, which is the absolute value of 4, which is just 4. And again, 1 unit plus the 3 units is 4 units. All right, so that's length. Congruent segments was our first, I think the first time we're mentioning the word congruent. We have a lot of C words. We had concurrent already. We have congruent. We'll have complementary later on, so make sure you know the difference between all of those. Congruent segments are segments with equal lengths. You see the symbol there for congruent. Mine doesn't look as nice as that all the time. You just make an equal sign and put a little squiggly on top of it. So that is your congruent symbol. And just to mention it now, and I will mention it more later, objects can be congruent to each other, whereas measurements are equal. So objects can be congruent whereas numbers and measurements, because a measurement is a number or uses a number, can be equal. So congruent and equality or equals seem very similar, but they are not exactly the same. All right, so that's congruent segments. We can mark, so I'll try to sketch a pair of congruent segments. So I was trying to make those exactly the same length. I'm not perfect, so what we can do to show they're congruent is you can put the same amount of little tick marks on there. And so if we label our endpoints here, we could say segment BD is congruent to segment RK. That says the two segments are congruent. They're the objects, but we can also say BD, which I'm not putting anything on top. That means the measure from B to D is equal to the measurement from R to K, or length RK. So we have similar concepts, but they definitely are different. Now we have another definition, this idea of between. And between in geometry is a little more specific than what we would use between for in our everyday life. If I had picture of a triangle, and then a circle, and then a rectangle. I might say that circle is between the triangle and rectangle, but in geometry, it is not between. In order for it to be between, it would have to lie on the same line. So I would have to put this, it would have to be right between them, lie on the same line. It doesn't have to be right in the center, just on the same line. So I'm going to erase those. But so what this says, point B is between, so we'll say the word between. Sometimes we will actually say betweenness. B is between A and C with a notation of A hyphen B hyphen C. So I read this. So we don't even read it in order. We say B is between A and C. That's how that symbol there gets translated. If AB plus BC equals AC. So let's take a look at this. Here's A and C, and this is B here. Notice B does not have to be exactly in the center, which we'll talk about later. It can be anywhere on that same segment, but AB plus BC equals AC. Now I want to show you kind of a contrast. If B was up here, we might say, oh, well, B kind of looks like it's between A and C, but it's not, because AB plus BC would actually be longer than AC. And we can think of that if we were trying to walk from A to C, it would take longer to take this orange route than it would to take the black route. So that's between. So in this example 2, we're going to try to use this idea of between. It says find AB, so that's the length from A to B, and BC, which is the length from B to C, because there's no symbols on above those, if AC is 75. So it's telling us this whole thing is 75. Well, since B lies on the same line there, it's between, we can say AB plus BC is equal to the whole thing AC. Now, I'm writing a few steps in here that might not be necessary, but that's what we can write because of betweenness, because it's between. Well, what is the length of AB? Well, we see that AB is 6x minus 1 plus BC, which is 5x plus 10, is equal to AC, which is 75. And now we have an algebra question to solve. So we have some like terms. 5x plus 6x is 11x. Negative 1 plus 10 is 9. Equals 75. We're running low on room. I'm going to try to squeeze it in. I'll make it a little bigger for you. So let's go ahead and subtract 9 from both sides. $75 minus 9 is 66. So 11x equals 66. Divide both sides by 11. I'll rewrite it. 11x equals 66. Divide both sides by 11. And we get x equals 6. And we might think, great job, we found x, we're finished. But we're not finished, because we have to look back at the directions. And it actually says find AB and BC. So AB, well, we know AB was equal to the 6x minus 1. So we put that 6 back in there. So 6 times 6 minus 1 That's 36 minus 1 is 35. And then we're also going to find BC. BC, that was 5x plus 10. We're going to plug x in. This 30 plus 10 equals 40. So there's my two answers. And actually, I have a great way to check this. What should these two add up to equal? Well, they should add up to equal 75 because that's the whole thing, and they do. So AB equals 35 and BC equals 40. All right, that was between. So realize B was not right in the middle. It was just somewhere along there. Other times it might be really close to A, or sometimes it'll be close to C. Maybe sometimes it will be close to the middle. But being between doesn't have to be right smack dab in the middle. That's what the midpoint has to be. So now we are referring to or learning about midpoint. Point M is the midpoint of XY if we have to settle two things here. It has to fit two characteristics. M is the midpoint of XY if, remember how to read this, M is between X and Y. So Y has to be between it, but that's not the only thing. It also has to be that XM is equal to MY. So M's between it, but we also know that it splits it into two segments that are equal, or, actually this isn't even written correctly. If I'm going to use congruent, I have to use segments. All right, so for it to be the midpoint, it has to be between them, and those two segments have to be equal. Notice they're both marked here with a red. Now I'm changing it to orange. One orange tick mark. Or I could have done like 3 to show, hey, that segment there, XM, is congruent to MY. So midpoint does go exactly in the middle. So that was segments and measures of segments. Now we're going to get to angles. And the way that we learn to measure an angle is we use degree. There are other ways to measure angles, but what we're learning for right now is degrees. So a degree, it's really not an amazing definition. It's just, it's 1/360th of a complete rotation. Now, where did this idea of 360 come from? Well, I've asked classes in the past, and some of them have come up with this idea, and some of them haven't. And so I try to hint to them, what is 360? What important number is that close to in our everyday lives? Or maybe I'll give you a hint and say every year lives. So this is close to 365, which is how many days are in a year. And so degree, it seems like the Earth rotates about 1 degree per day. Remember, here's the sun. And then the Earth, these are not drawn to scale, and just put a little green on here for a continent or so. The Earth rotates around the sun in an almost circular orbit. It takes, so in one day, this travels about 1 degree. Definitely not drawn to scale, but that's the idea. That's why we think it's 360. But a degree is 1/360th of a complete rotation. Protractor postulate says any angle A can be placed in a 1-to-1 correspondence with a degree measure less than or equal to 180. So any angle can be measured from 0 to 180 degrees. We have some classifications for our angles, which you've probably heard before. An angle that's between 0 and 90 degrees is called acute. So there's an acute angle. There's an acute angle. Here's one that's still acute, getting closer to not being acute, but those are all acute angles, less than 90, between 0 and 90. Then we have a right angle. That's only one spot. It's a right angle, 90 degrees. We mark it with a little square. So that's what this is saying. Right angles are indicated with a symbol. That's the symbol we're referring to. Obtuse angles are between 90 and 180 degrees. So they look something like that. And then a straight angle equals 180 degrees. A lot of times we put a point here to show that we have an angle. So that's equal to 180 degrees. Now this protractor here is pretty blurry, but notice that there are two sets of measurements here. We have the inner ones, and then we have these outer ones. You use whichever ones make sense to use. So if, and not all protractors are the same, but if you had an angle and if it was on a protractor like this, here's 0, we would want to use the outer one because our ray here is at 0 and we would work our way up. So this looks like it would be an 80-degree angle. I know it's very messy or very unclear, but that was an 80-degree angle. So that's how you use your protractor. Make sure you use the correct part of the protractor, the inner part or the outer part. Now you should be able to figure that out by looking at it. You should be able to tell, hey, this is an acute angle. Keep messing up there. This is an acute angle, so it's got to be less than 90 degrees. All right, segments. We're right here now. Segments, rays, or lines that intersect to form right angles are called perpendicular. Our symbol for perpendicular is this symbol that looks like an upside down capital T. So that's when it's 90 degrees. Two lines, rays, or segments intersect at right angles. All right, we're going to use this protractor here. Again, not real clear, but we're going to use this protractor here to help find some measures. So angle BAC. BAC. So right now I'll highlight it. So it's starting on this side, which means here's our 0. So we're going to use the inner measurements. And what's this going through? Well, it's going through 60. So that is a 60-degree angle. The directions also say classify it as acute, right, obtuse, or straight. Well, it's less than 90, so it's acute. On to the next one. Maybe I'll just use a different color instead of erasing. EAB. So here's point E, here's point A, and point B is up here. So we're looking at this angle. Well, now we're starting on the left side of the protractor. And we're looking at this angle. So we need to use the outer loop because that's where our 0 is. We're going outer. Well, outer, we're at 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. So this is a 120-degree angle. Well, that is obtuse. And now lastly, we're going to go angle BAD. BAD. Well, it's interesting because neither of those start at 0. So what we're going to do is we're just going to subtract. We can pick either inner or outer, whichever. So let's say we pick the inner. That's at 150. And stay with the inner. This one here is 60. We can say this is going to be 150 degrees minus 60 degrees, and that is 90 degrees. Well, that's a right angle. All right, congruent. We learned the word congruent earlier with congruent sides. Now we're talking about our segments, sorry. Now we're talking about congruent angles. Congruent angles are angles with the same measure. Let's go ahead and try to sketch two congruent angles. The way that we mark angles congruent are putting the same arc markings in between them. So those two angles would be congruent because I have them marked congruent. Again, objects are congruent or can be congruent, whereas measurements are equal. So we see that again here. This is talking about the object angle X and the object angle Y. They're congruent to each other, whereas measurement of angle X and measure of angle Y are equal to each other. Notice down here, these are both marked the same with the same arc. It also does tell the measure there, but that's how you tell if things are congruent. Sometimes you'll even see like this angle, if we want these two, they might have like two arc things with one in between, as long as they're marked the same. So congruent angles are angles that have equal measurements. Few more terms and then we'll be finished. Adjacent angles. It's a word we hear in our English language, and it is similar to what we're doing here. If you're in a room and there's a room next to mine, those two rooms we also say are adjacent, not the one across the hall, but the one that shares a wall. They would be adjacent. Well, adjacent angles share a vertex and share a side, which is a ray, but they don't have any common interior points. So then we have this angle over here, and we'll choose a different color over here. So in our picture here, we could say angle MNK is adjacent to angle PNK. So those are adjacent angles. They share a vertex and a segment, but don't have any points in the interior in common. All right, the angle addition postulate is actually very similar to our definition of between. If K lies on the interior of angle MNP, all right, here's point K. It lies somewhere on the interior of angle MNP. We can say that the smaller angle, the two smaller angles, which are MNK plus KNP, is equal to the measure of this larger angle. So that whole thing there. So it's equal to that measure of that larger angle. And we'll see that in this example here. Example 4, find the measure of angle 2 if measure of angle BAD, that's the large one, the measure of angle BAD, that whole thing there, we want to find that if the measure of angle 1 is 155, or is 55. So measure of angle 1 is 55. Well, notice that they have both the same markings. They have both these two arcs, which means those two angles are congruent, which means the measures are the same. So we know the measure of angle 2 has to equal 55 as well. And then we can say measure of angle BAD has to equal those two smaller ones added together, 55 plus 55, which is 110 degrees. Should put our degrees there. So there's our two answers. And so that was measurement. We did measurements of segments and measurements of angles.